Welcome to the deep dive. Today, we're focusing on a safety issue that's literally running overhead right now, wherever you are.
Yeah, that's a good way to put it.
We're tackling what might be the most dense standards document in electrical safety, the National Electrical Code.
Specifically, the 2023 edition, NFPA 70.
Exactly.
And it's easy to dismiss codes like this as just, I don't know, bureaucratic hurdles. But the NEC is really a rule book written in blood. Every single line is there to prevent an injury or a fire.
That's a powerful way to think about it.
And our mission for this deep dive is highly specific, almost surgical.
Okay.
We're cutting straight into Chapter 2, Wiring and Protection, to decode just one specific rule, the one that governs how close overhead electrical conductors can safely get to a building.
So this is your absolute shortcut to understanding a critical area of compliance. If you're involved in construction, renovations, or just want to understand why that wire running next to your garage is placed exactly where it is.
This is the deep dive for you.
And we should be clear, we're pulling all these insights directly from the official 2023 NEC text and its commentary.
Okay, so let's unpack this standard, but first we need a little context.
Right.
Instead of seeing the NEC as this massive, intimidating list of rules, think of it more as a comprehensive solution manual.
Solution to what?
To the problem that's always there. How do we safely deliver electricity from the utility all the way to the point of use?
That reframing really helps. So within that solution manual, where does our focus today, Chapter 2, fit into the whole structure?
Well, Chapter 2, Wiring and Protection, is arguably the core foundation for any safe installation. It comes right after Chapter 1, which covers all the general rules.
And before the more hands-on stuff.
Exactly. It precedes chapters like Chapter 3, which gets into specific wiring methods, or Chapter 4, which is all about equipment. So Chapter 2 sets the essential boundaries.
Boundaries like what needs to be protected, how far away things have to be.
And what those protected materials actually have to be capable of.
So Chapter 2 is really the framework for safety, geometry, and material integrity.
That's a great way to say it.
And the specific rule we've targeted is Section 225.4, Conductor Insulation. This is where that geography of safety meets the physics of electricity.
That's precisely right. Section 225.4 establishes what we can call the mandatory protection zone around any building or structure.
Okay, protection zone.
And it deals with conductors that are open and aerial, wires just suspended in the air.
Here's where it gets really interesting because the code gives us a hard-defined distance. For anyone listening, what is that critical threshold that triggers this mandatory insulation?
The rule is extremely precise. Open individual overhead conductors, they have to be fully insulated for the nominal voltage if they fall within 3.0 meters.
3 meters, which is about 10 feet.
10 feet, exactly. 10 feet of any building or structure. This is a non-negotiable safety corridor.
So if a conductor is bare or just sort of covered without proper insulation, it just cannot enter that 10-foot boundary.
That's the rule.
10 feet is a standard we hear all the time in construction safety. Why that specific distance? What's the danger that 10-foot boundary is trying to prevent?
You have to think about accessibility and incidental contact.
Right.
The 10-foot rule protects against common scenarios. A homeowner using a ladder for painting or roof repair.
Or trimming a tree branch that might swing near the wires.
Exactly. Or even fire department access routes during an emergency. 10 feet is generally considered the distance you need to keep unauthorized or just accidental contact from happening.
So it's the zone where human activity is most likely to intersect with power delivery.
Right.
Now, you said the rule applies to any building or structure.
Yeah.
What about the pole holding the wires up? Does that count?
And that's the critical nuance. The code anticipates that question.
Okay.
It specifically excludes supporting poles or towers from being counted as the structures that trigger the 10-foot rule.
So the focus is on proximity to walls, roofs, balconies, places where people would actually be.
Right. Not the utility infrastructure itself. The integrity of the building's envelope is the concern here.
That clarifies the focus perfectly. So moving past the distance, once a conductor does enter that 10-foot zone, the code gets very prescriptive about the quality of the insulation.
It does.
It's not just any plastic coating.
Absolutely not. This rule demands high performance. For conductors and cables or raceways inside that zone, the insulation has to be of the thermoset or thermoplastic type.
For someone who hears those terms and just thinks, okay, technical jargon, what does that actually guarantee? What makes them so special?
That's a great question. This is where we link the code to the function. Thermoset and thermoplastic materials are chosen because they offer Well, superior resilience.
compared to older stuff.
Right. Thermosets, for example, maintain their shape and integrity even when they get really hot, like from direct sun or an overload, they won't melt or deform.
And thermoplastics.
Similarly, they offer excellent resistance to moisture, chemicals, physical abrasion. In short, this material requirement ensures the insulation won't degrade quickly from UV exposure or environmental stress. It keeps the conductor safe for decades.
That makes the requirement much more meaningful. But, in the world of electrical code, there's always an exception. I see that one specific cable type MI cable is exempt.
It is.
Why does mineral insulated cable get a pass on this?
It's an exemption based on its intrinsic safety. Type MI cable is just fundamentally different. It uses highly compressed mineral insulation, magnesium oxide inside a seamless copper or stainless steel sheath.
I see.
So because that sheath itself is grounded and the mineral insulation is non-flammable and incredibly durable, it achieves that protection level through its own construction. The extra polymer requirement is just redundant.
So it's safe just by a different engineering standard.
That's it, exactly.
That's a great insight into the logic. Now let's talk about the environment. Being close to a building often means exposure to the elements. What happens when these conductors are in wet locations?
Right. If those installations are in wet areas, think outside conduit runs or places with constant condensation, they face an additional mandate. They have to specifically comply with Section 310.1c.
And without having us memorize the whole section, what's the core requirement there?
310.1c simply governs the types of insulated conductors that are allowed for use in wet locations.
So they have to be specifically rated for it.
They have to be listed and rated for damp or wet environments. The goal is to stop moisture from compromising the insulation, which could lead to shorts, ground faults, or, premature failure.
And as we've noted, the NEC is incredibly comprehensive. It even covers temporary or decorative lighting.
The fun stuff.
Yeah, festoon lighting. Does the same strict material requirement apply there too?
Absolutely. Safety standards don't take a holiday for aesthetics. The insulation for festoon lighting conductors must also be of the thermoset or thermoplastic type.
So whether it's temporary wiring for a market or a permanent service drop, the risk is the same.
If it enters that 10-foot zone, the risk of incidental contact is the same, and the insulation has to hold up.
Okay, so we've established a very clear, rigid standard for all energized overhead conductors in that zone. Mandatory, specific insulation. Now let's flip that coin and talk about the conductors that are explicitly not energized under normal circumstances.
Grounding wires.
Exactly.
This is a crucial distinction. It gets to the heart of electrical safety logic. The strict insulation requirements are all about preventing arc flash and shock hazards from the live wires.
But these are different.
When we look at the exceptions, we're defining conductors that serve a safety function, not a delivery function.
So what's the allowance for equipment grounding conductors and grounded circuit conductors?
This is where the code provides some flexibility. These types of conductors are permitted to be bare or covered as allowed elsewhere in the code.
They don't need that same rigorous thermoset jacket.
Nope. Because inherently, they're either at zero potential or are designed to safely carry fault current back to the source or to the ground.
So connecting this to the big picture for you, the listener, this means that while live power lines need that robust insulation in the 10-foot zone, the wires designed just for fault protection don't. Why is it okay for them to be bare?
Because their main purpose is to bond metallic parts together and facilitate the opening of a circuit breaker if a fault occurs.
So they're only energized during a fault.
Exactly. And even then, their entire function is to maintain a low impedance path to ground. Adding expensive insulation to a conductor that is purposefully meant to be at zero voltage most of the time is just, deemed unnecessary by the code.
It's a pragmatic approach.
It is. It focuses resources on insulating the dangerous parts while allowing simpler methods for the inherently safe parts.
That really highlights the critical safety distinction the NEC is trying to make. Compliance means understanding the difference between the wires that deliver power and the wires that deliver protection.
Precisely. If you're inspecting a job or designing an installation, seeing a bare conductor near a structure is immediately okay if it's a grounding conductor.
But if it's a live phase conductor,
And it's within that 3.0 meter boundary, it is a mandatory violation unless it has that specified insulation. Knowing Section 225.4 is knowing the line between compliant safety and potential liability.
and that brings us to the core takeaway for you. We dove into the NEC 2023 Section 225.4, and the key understanding is this. 10 feet from a structure is a hard safety boundary.
A hard boundary.
Inside that zone, energized conductors demand that thermoset or thermoplastic insulation for resilience. But those grounding and grounded conductors, they're permitted to be bare or covered because of their safety function.
What's fascinating here is how these simple numbers encapsulate really complex risk assessments. The very existence of this mandatory 3.0 meter protection zone raises a deeper question.
What's that?
If we mandate these specific insulation types and distances to protect people, what unseen costs in maintenance, insurance, liability are we mitigating just by adhering to a seemingly simple numerical standard?
So it's not just about the distance itself.
Right. This 10-foot rule isn't just about physical distance. It's a calculation of acceptable risk based on human behavior and environmental exposure. It forces us to recognize that these standards are always calculated risks, something to mull over the next time you look at a wire running near a structure.
Excellent point. Thank you for joining us on this deep dive into the structure of safety. Until next time, stay curious.